Dear friends, this is the lecture number 4 of electromagnetism. In the previous lecture, we discussed about the moving charge in uniform magnetic field, how it experiences force and what is the trajectory. But today we'll discuss about Lorentz force and force on a current carrying conductor. Also parallel currents and torque on a current carrying loop. So let's come first to Lorentz force. Lorentz force. So in previous class we did the comparison of force on a charged particle due to electric field as well as due to magnetic field. Though it is same, though there is some similarity, but also there is many dissimilarities. We discussed everything in the previous lecture. When the charged particle is in electric field, how much force acts? F is equal to QE vector. When the charged particle is moving in magnetic field, how much force acts? F is equal to Q whole into V vector cross E vector. Now the time comes here to mention clearly about this F, because now this is F, this is F. One day this was separate, one day this was separate, but now when both comes into action, so when both will come to action, we have to write this is E for electric force, M for magnetic force. Both apply on both electric field and magnetic field apply force on the charged particle. But what do we mean by Lorentz force? When a charged particle remain in a region of both electric and magnetic field. Suppose in a region both electric field and magnetic field are present. Two fields are present simultaneously in the same region, and one charged particle enters inside. That charged particle will experience force. No field will give excuse to the charged particle. Both will apply force on the charged particle, and the total force is called as Lorentz force. Lorentz force is the force experienced by the charged particle in a region of both electric field and magnetic field. So what is Lorentz force? So Lorentz force, I am writing the symbol with L. It is electric force plus magnetic force. Electric force Q E vector and magnetic force Q whole into V vector cross B vector. Both forces when act, then this is called Lorentz force. Also, if one single force acts, this force also can be called as a Lorentz force. If electric force is 0, if this is 0, then this also can be called as Lorentz force. But when both fields are present at one place, the sum of total is actually called Lorentz force. Okay, from this Lorentz force, now we'll discuss about velocity selector. Now let's come to one application of this velocity selector. Let's come to the application of Lorentz force, that is the velocity selector, or this is also called as filter. This is also called as a filter, charge filter. You can say velocity filter. It filters something. Its name is filter. So now discuss it. What is this velocity selector? Suppose you consider a region. This is a region where uniform magnetic field exists. One magnetic field exists in this region. When this magnetic field exists in this region, one charged particle, suppose one charged particle Q enter in the field. This is positive charge. Is now entering into the field. When the charged particle Q enter, magnetic field will apply force. Okay, how much force the magnetic field will apply? Fm is equal to Q whole into V cross B, where V is the velocity of the charged particle and B vector is the magnetic field strength of the uniform magnetic field. What is the direction of this force? We can determine by Fleming's left hand rule. I told you in the previous lecture, in the left hand, this one represents force. You see, I have written. So you always also keep writing, at least when this chapter is going on. Okay, so here F, this is M, magnetic field, and this is C, current, motion of positive charge. Okay, so now comes here, if this is the magnetic field inside, I told you always first feed the magnetic field. Magnetic field, this is the charge, this is positive charge, no problem. So positive charge, where is the direction of the force? Is it clearly visible to you? I think the direction of force is now upward. Thumb is upward. So this is the direction of the force. In this direction, force acts this magnetic force. But another electric field is also present in that region. The electric field is present like this. Electric field lines are like this. See, electric field is present in that region. So uniform electric field it is, where the direction of the electric field is in downward direction. This is the electric field intensity E vector. If the charged particle is in electric field, then also force acts. And electric field will apply how much force? Q E vector. But where is the direction of the force? Direction of the force is along the electric field if Q is positive, opposite to the electric field if Q is negative. You recall the first chapter. Okay, but here Q is positive or negative? Positive. If Q is positive, force will be along the electric field. Electric field direction is downward. Also force will be along the electric field, that means it is downward. So this is your electric force. Now you see the situation, see the direction of the two forces. They are in opposite direction. If the two forces will be equal in magnitude, then they must cancel each other. Now the two forces cancel each other because they are opposite in direction. Only if the magnitude will be same, then they cancel each other. If they cancel each other, what will the net force on the charged particle? Net force on the charged particle is equal to 0. Net force on the charged particle is equal to 0 if the two forces cancel each other. If the net force is 0, then the particle moves along the direction of its motion. You see, with the constant velocity, the particle will move like this. It goes undeflected. It will not deviate from its path. What is situation? The region has electric field and magnetic field. Both fields are there, but the particle is going undeflected. How this happened? Because the two fields actually apply the force, but the two forces are in opposite direction. So net force cancel, it goes undeflected. So now see, let's find that velocity. With how much velocity it should enter so that the two forces will be equal in magnitude. Let's find that velocity. So when Fe is equal to Fm, then it goes undeflected. So here Fe is Qe and Fm is Qvb and Qq cancel. So that velocity is E by V. So this is the expression of velocity. Sometimes the question comes in exam. With how much velocity a particle should enter in crossed electric and magnetic field so that it goes undeflected. The simple formula you can use E by V. Electrical intensity divided by magnetic field intensity, E by V, meter per second. So if with this much velocity the particle will enter, it will go undeflected, without any deviation from its path. Suppose the same particle Suppose the same particle now enter, or any particle here doesn't matter which particle is moving, because you see Q cancel. But positive that should be, if the direction of field is like this, then charge should be positive. So if any other positive particle enter with more than this velocity, then what happens? If the velocity will be more, you see the expression of two forces, which force depends on velocity. Now you come to case 1. Case 1. Suppose velocity is more than this velocity. Let's take velocity v1. With v1 velocity, suppose it enter, which is more than your this velocity, your undeflected velocity. If velocity is more, then which force depends on velocity? Electric or magnetic? Magnetic force. If velocity will increase, then magnetic force will increase. See here clearly, try to understand. So if velocity increase, here no velocity. But if velocity will increase, the magnetic force will increase. Now you see magnetic force increase. If magnetic force increase, the particle will be deflected in which direction? The particle now is deflected in upward direction like this. This is the velocity v1, which is greater than your this velocity, undeflected velocity. But case 2. Come to case 2. If velocity will be less than this velocity. See, velocity increases, I have v2. If velocity decreases, If velocity decreases, then this force decreases. Fm. If velocity decrease, then magnetic force only change. Electric force is constant. If velocity decreases, then Fm decreases. Fm less than Fe. So electric force is greater. If electric force is greater, then the particle deflects in this direction. So now see how it is used as a velocity selector or velocity filter. There is no explanation till now. I gave you from using these two terms, but you could be able to understand. If this v velocity comes, it goes undeflected. More than v, it goes upward. Less than v, it goes downward. Situation is like this. But how to use your velocity selector? Suppose you are doing some experiment or something. You need a particle of a particular velocity. Okay, how much velocity? Suppose you need a particle, I am giving you the example, 10 meter per second. If you need a particle of 10 meter per second, for example, I am telling you. If you need a particle of 10 meter per second, you choose your electric field as suppose 100 Newton per Coulomb. Choose your magnetic field as 10 Tesla. Now you see E by V 100 by 10 is equal to V. E by V 100 by 10 is equal to V. You choose your electric field like this, choose your magnetic field like this, take your particle. So now 100 by 10, this is 10 meter per second. Okay, you need a particle of speed 10 meter per second. So the particles, many particles what you produce by some device, the particles are coming now. But you don't know that which particle is coming at a speed of 10 meter per second, that you don't know. But you know many particles are coming with different velocities. But when the particles will come to this situation, as this ratio E by V is 10 meter per second, undeflected velocity is 10 meter per second, the particle which has velocity 10 meter per second, it go undeflected, means own way. You inject the particles through this line, who now go straight through the line of injection of the particle, that is 10 meter per second. Who will go deflected upward direction, that is more than 10. Who deflected downward direction, less than 10. But you got your desired particle, you need a particle of 10 meter per second, that goes straight. With how much speed particle you need, accordingly you have to set E value and B value. E by B ratio is equal to speed of the particle. So like this, that means when many particles of different velocity comes, they get filtered here. We filter the particles here. We get only the particle of E by B speed, means 10 meter per second. So Is it used as a velocity filter? Is it used as a velocity selector? So this is the main mechanism of velocity selector. And based on this, your spectrometer works. Based on this. Okay, so that's the application of this. It is used in spectrometer. Then let's come to the force on a current carrying conductor. When a current carrying conductor is kept in uniform magnetic field, it cannot remain stationary. When current passes through it, it cannot remain stationary. It gets deflected. Why it gets deflected? Because force acts on it. Why force acts on it? Why force acts on a current carrying conductor? Current carrying conductor behaves like a magnet. Current carrying conductor has its own magnetic field, and when we will keep it in external magnetic field and magnetic field interaction happens. So force acts on the current carrying conductor. My question was, why force acts on a current carrying conductor in uniform magnetic field or in magnetic field? Because current carrying conductor has its own magnetic field which interact with applied magnetic field. So force acts on current carrying conductor. Okay. Otherwise we can say also this one in another way. What is another way? In current carrying conductor, what is inside? What move inside a conductor? Charges move. You know, charge when move, it is moving inside the conductor, but it is kept in magnetic field. Means charge is moving in magnetic field. When charge is moving in magnetic field, force acts on it. And when force acts on the charge, means there are many number of charges. Force acts on all charges. Force acts on all charges means force acts on the conductor because the charges are inside the conductor. Force actually acts on the charges. F is equal to Q whole into V plus B. As many number of charges are there, force acts on all charges. Hence force acts on the conductor. We can say also in this way. Then question is coming to your mind. When the conductor is just lying, no current pass, it is just lying, no current. Just it is present in the magnetic field. No current is given to this conductor. There also charges move or not? There also charges move. Means force acts on this conductor. When no current is given, current is equal to 0. It is in magnetic field. Then force acts. Now the question is coming to your mind. If the conductor is just kept like this, no current passes through it, force acts on it or not. If you do the experiment, you will see no force acts on it. Why? Charges move inside it, but how force doesn't act on the conductor? Does force act on charges? Yes. When the no current passes, still charges are there, and you know charges not, they don't remain at rest, they also move inside the conductor even when no current passes. So force acts on charges, but force do not act on the conductor. Why? Because the charges move in rapid random motion in different direction. Force acts on charges, but those forces cancel each other because there is no specific direction of force, because there is no specific velocity of charges. Charges move randomly. When charges move randomly, force is also random, so all the forces cancel each other. But when current pass, then you know charges move towards the positive terminal, they get drifted towards the positive terminal, electrons get drifted towards the positive terminal. Now they have a specific direction is coming, so the forces direction also will be same. Now net force cannot be 0, so force acts on the conductor. So my question is now how you calculate how much of force acts on the conductor. So this is the conductor lying in magnetic field. This is suppose magnetic field present. The conductor is lying in the magnetic field. So I told force acts on the conductor because force acts on the charges. Because force acts on the charges. So let's consider dq amount of charge. Very small charge, inside it dq is moving. Let's calculate force on dq amount of charge. Okay. So what is the force experienced by dq amount of charge? Obviously this is df q whole into v cross b. So dq vt cross b. Why vd? Because drift velocity. The electron's velocity is drift velocity will take. So this is the force act on dq amount of charge due to the magnetic field. So here dq, but what about vd? Vd can I write this is dl by dt cross b. Vd I am writing here dl by dt cross b. So dt taken to outside. So this is dl cross b. So what is dq by dt? So this is I dl cross b. Now you integrate both sides. Integrating both sides to find the net force on the conductor which is inside the magnetic field of length L. How much length is inside the magnetic field, that is important. Force act on that length. So integrating both sides, df integration is f and I dl integration is L. How much length is inside the magnetic field. So this is the force act on the current carrying conductor of length L. But if you write the force magnitude, so it is I L B sin theta. But easily you can remember the force like this. I rearrange the letters. Bill sin theta. What is the force act on a current carrying conductor? Bill sin theta. You remember it like this. Bill sin theta. As theta is there, then another thing also, direction of force from the cross product rule. It's very clear. Force is directly proportional to L, and force from the cross product rule, not direct proportional. Okay, force from the cross product rule, direction of force is perpendicular to L and perpendicular to B. Force is perpendicular to L and force is perpendicular to B. This is from the direction of force, cross product rule. Okay, so then we'll discuss the cases. As theta is there, come to case 1. So means your force act on the conductor is perpendicular to the length of the conductor. Remember this one. Force always perpendicular to the length of the conductor. Theta is equal to 0 or 180. What is the force? 0. Sin 0, 0, sin 180, 0. Means conductor when it is kept along the magnetic field or opposite to magnetic field, no force act on the conductor, though it is in magnetic field. Case 2. Now come to case 2, theta 90 degree, F is equal to, this is Bill, sin 91, F is equal to Bill. This is the maximum force and this is the minimum force. Direction of force in this case, we can determine by Fleming's left hand rule. Direction of force we can determine by Fleming's left hand rule. The same thing. This one force, this one magnetic field and this one current. By Fleming's left hand rule we can determine the direction of force. So we now conclude here the force act on a current carrying conductor is Bill sin theta, or in vector form I whole into L cross B. So then come here force between two parallel currents. How force acts between two parallel currents. Why force will act between two parallel currents? There is no magnetic field. Let's consider two parallel currents like this. This is one current. This is one current. Two parallel currents. One current is I1. One current is I2. The separation between the two currents. Let's start the separation here. Separation between the two currents is D. Why two currents will apply force on each other? You know when a current is kept in magnetic field, force acts. But why do currents apply force on each other? Why? It's very simple. You think the answer. Think the answer, then again you play this video. Why force acts between two currents? Okay, I'm telling you the answer. This current carrying conductor behaves like a magnet. It provides its magnetic field around it. Within its magnetic field, this conductor present. Force will act. Come to this one. This current carrying conductor I2 behaves like a magnet. It provides its magnetic field, and within that magnetic field this conductor present. So force acts. So it's a mutual force. I1 apply the force on I2, I2 apply the force on I1. So in the magnetic field of one conductor, as other conductor is present, so force acts between two parallel currents. Let's find how much force acts between two parallel currents. So I1, I2 are two currents placed in vacuum. I am taking the medium vacuum, so D is the distance of separation. What is the magnetic field due to I1 on I2? So let's find the force on I2 due to I1. Force on I2 due to I1. So means we have to find I1 magnetic field on I2 here. Here, what is the magnetic field? At this, on this conductor here, on this conductor, due to this current, due to I1 current, what is the magnetic field here? These are infinite currents. Infinite currents these are. At a distance d, what is the expression of magnetic field? You have derived using ampere circuital law. For infinite conductor using ampere circuital law, also you can derive using Bart-Savart law also. The magnetic field expression at a distance d outside the conductor. This is thin conductor, outside it, so magnetic field. So V1 mu naught I1 divided by 2 pi d. Am I correct? Mu naught I by 2 pi r. So mu naught I1 by 2 pi d. This is the magnetic field due to this conductor. But where is the magnetic field? Direction. Where is the direction of magnetic field? Magnetic field, if current is passing like this, magnetic field will be inward. Magnetic direction I can show it here to you. This is the direction of magnetic field of V1. What is the angle between this magnetic field and this length of the conductor? Because that is important while calculating force on this conductor. That is important. That when you think what is the angle between V1 and this length of this conductor I2. Now let's see. This is the magnetic field of this conductor. What is the force on I2? What is the force on I2 due to I1? Force on I2 due to I1. Due to I1, what is the force? So due to I1 means I am writing F21. I am writing only magnitude first. F21 force on I2 due to I1. Formula is Bill sin theta. Bill sin theta. But this magnetic field is of which conductor? Of I1. Because I1 magnetic field, force on I2. So this is 1. This current, as I2 experience the force, current is obviously of I2. Length is also of I2. Because I2 will experience the force sin theta. But what is the value of theta? That I need. What is the value of theta? That is important here. From the figure, can you able to mark what is the value of theta? Okay, it's very difficult from the figure to mark because this figure will be a 3D figure, but I have to run it on 2D. But I am showing you the 3D. I have one arrangement to show you. You see. So these are the two conductors. Okay. So now one is the black conductor, one is the green conductor. These are the two conductors, black conductor and green conductor. Suppose black conductor is the one conductor. I am drawing the figure, you see. Black conductor is this is one conductor, first conductor this is the second conductor. Force will apply on second conductor. Force will find on second conductor. But this conductor will provide its magnetic field. Okay. So how its magnetic field lines will be? circular lines. Magnetic lines will be circular. So in which direction the magnetic lines will be? Now let's see. We have to use which law here? Current is going like this. So you see, current is going like this. Thumb rule. So this is the direction of a magnetic lines of forces. Its magnetic lines of forces. Clear? If current is going in this direction. Okay. So now I'm drawing the direction of magnetic lines of forces. You see. Circular direction magnetic lines of forces, though it is not perfect circle, but you manage. It will be circular to that side, circular that side, circular, you see, to that side. So these lines of forces are of a magnet, are of a current 1, and the direction is in this direction, here in this direction. Okay, here in this direction, here in this direction, here in this direction. Okay, if the lines of forces are like this, where is the direction of a magnetic field? Exactly on the I2, on I2. Here, where is the direction of magnetic field? Magnetic field will be along the tangent. So this is the tangent. This is the tangent. This is the direction of the magnetic field of a 1 vector. You see, B1 vector. This is the direction of magnetic field of a B1 vector. Okay, this I1 current provides the magnetic lines of forces, and this is the direction of the B1 at this point. If this is the direction of a B1 along the tangent, now you can able to mark here. This is the length of a second conductor, I2. What is the angle between length of the conductor and the magnetic field? It's very clear to all of you now. See. What is the angle between length of the conductor and magnetic field? This is the angle. In 3D now, it's very clear to see the angle between length and magnetic field. But here it is little difficult to see, but here it is very clear. How much is the angle? Okay, so the angle is here now 90 degree. I know you could able to understand. So we'll put here B1 expression mu naught I1 by 2 pi d, then I2, then A, then sine 90. Okay, so mu naught I1 I2 divided by 2 pi d, but I am bringing the length to this side. I am bringing the length to this side. Sine 90 is 1. Why I am bringing the length to this side? Because it is an infinite conductor. Force on the conductor doesn't matter. That is not important. Rather, force per unit length of the conductor matters because it is infinite conductor. Force per unit length of the conductor, that matters. If this conductor will be finite, then the length will keep at this side to find the net force. If the conductor will be finite, then this L will keep at this side. If this conductor is infinite, we will take the L to this side, no problem. But mu naught I1 I2 by 2 pi d is not the expression of force. This is the expression of force per unit length. Keep in mind, force per unit length. Okay, so this is the force per unit length we derived on I2 due to I1. Similarly, I am not going to derive the other one. Similarly here, force on 1 due to 2 per unit length. If we do, then I1, I2 here will be alter only. So this will be I2 by 1, 2 by d. Both expressions are same. Means both conductors apply same force on each other because it's a mutual force. But where is the direction of a force? Where is the direction of F21, F12 when the two conductors are parallel, when parallel currents pass? Where is the direction of force? Also, to know the direction of force, we will take the help of the 3D. See here. We will take the help of this 3D. You can also make it at home in a paper. Okay. Then you can also check by using your fingers where is the direction. So force acts on this conductor. This is F21. F21 on the now green field. Okay. So here force acts. Now find the direction of the force. Play means left hand rule. Clear? Left hand. I need magnetic field is downward. Magnetic field is keep downward. Current is where? Current is to the front. See my finger arrangement. So current, magnetic field is downward and current is towards you. This is the magnetic field, this is the current. This finger is the current finger. This one is the current finger. Current is now along the pen. Magnetic field downward, current is along the pen. You see. Can you able to mark this arrangement? Okay, that is now visible to you. Okay, so here is the direction of force. Thumb is to which side? Thumb is to the first conductor. Thumb is towards the first conductor. See. So the force acts here towards the first conductor, means along this direction. F21. When the current passes in this, where is the direction of F12 now? See, where is the direction of force F12? If we see also that force, if we do its magnetic field there, then the direction of force will be towards this. Similarly, you can do that one. The direction of force will be towards this. F12. That means two conductors attract or repel. Very clearly, they attract each other when the currents are parallel to each other. When two parallel currents pass, the two conductors here, you see, the two conductors here attract each other. They attract when parallel currents pass. Similarly, if anti-parallel current will pass, if anti-parallel current, this conductor, now current will go inside. What happens if anti-parallel current will pass? Both conductors will repel each other if anti-parallel current pass. Both conductors will repel each other if anti-parallel current pass. Means what is your conclusion? Two parallel currents attract each other and two anti-parallel currents repel each other. When current passes through two conductors in the same direction, there is a chance they may attract each other. If the current will be of a high value, then they attract each other. You have seen in day-to-day life between two poles, the wires are going. Okay, when wires are going, suppose two currents wires are going in parallel, and if heavy current is going, the two currents may attract each other. There is chance of attraction between them. When the wires get slack, they may attract each other. To avoid this, what the electricians do? With a plastic rod, they bind the conductors so that they cannot able to attract each other. Also, they bind with a plastic rod so that when the air blow, okay, when air blow happens with a high speed, they will not touch each other. If they will touch, then sparking will happen, short circuit may happen, and that will make damage to the transformer of the street. This is also one reason when two parallel currents passes, they should not attract each other. To avoid the attraction between them, the electricians bind them by plastic rod. Okay, so this is about the parallel currents. How force acts between two parallel currents. But when this is a very important 3 marks derivation for CBSE board examination. If you tell me, sir, which 3 marks derivation is important out of the whole syllabus of 12th class, I will tell this one is the most important derivation which always comes in exam in 12th class board examination. But when it comes as a 3 marks question. How much we did today? This is 2 marks. This is 2 marks what I did now. Then where is there 1 mark left? Definition of ampere. The question will come, derive the expression of force between two parallel currents. Hence write the definition of ampere. Definition of ampere. So definition of ampere, how will bring from this? In the question will come, write definition of ampere. So one student, suppose in exam will write, it is defined as charge flows per unit time. We will get a big zero. Charge flows per unit time is right. But the question wants you have to write the definition of ampere from this parallel current concept. Okay, so how will I write this one? F12 by L or F21 by L, that doesn't matter. Or F21 by L, that doesn't matter. F21 by L mu naught I1 I2 by 2 pi t. If I1 is equal to I2 is equal to 1 ampere, D is 1 meter, then what is F21 by L? Mu naught you put 4 pi into 10 to the power minus 7, I1 I2 1 into 1, 2 pi D is 1, so pi cancel, so 2 into 10 to the power minus 7 Newton per meter because length is here. Then you will write the definition. After doing this much, you will write the definition of ampere. So 1 ampere is that current which when passes in same direction in two parallel conductors. 1 ampere is that current which when passes in same direction in two parallel conductors separated by 1 meter in vacuum, then they exert a force of 2 into 10 to the power minus 7 Newton per meter. Then they exert a force of or attractive force of 2 into 10 to the power minus 7 Newton per meter on each other. Two important words you will not forget while writing this definition. One is in vacuum. Otherwise, some teachers are cutting the mark here in vacuum, and the another term you have to write here attractive force. Don't forget to write those two terms. So this is about force between two parallel currents. So now discuss when four conductors are placed in uniform magnetic field, making a coil. What happens? Now let's discuss that one. This is uniform magnetic field. Four conductors are placed. Now we discuss what happens there. Four conductors are placed here. So I am making the conductors like this. The conductor, they are just forming a loop here. They are placed like this. Current passes. Current carrying four conductors forming a loop, forming a coil set. Rectangular coil I have made. Rectangular coil. Okay. When they are placed like this, A, B, C, D. Okay, this very small gap, then the current comes out, and one axis is there about which this conductor can able to rotate. One axis is there. Let's take this is XY axis through which about which this coil can rotate. Means we are going to discuss torque on a current carrying loop. Torque on a current carrying loop. So let's find four conductors are there. So length of the loop is L, breadth of the loop is B. Suppose the loop makes theta angle. Loop makes theta angle with magnetic field. The surface of the loop makes theta angle with magnetic field. Four conductors are there. Length L and breadth P. Theta is angle, and the area of the conductor obviously will be L into B. L into B. So now let's find individually what force acts on each conductor. Four conductors are there on each conductor. Force on AB. First find force on AB. F1 vector. So that is I whole into L vector cross B vector. L vector cross B vector. And where is the direction of force? Left hand rule. This is the magnetic field. This is the current. Okay, this is the magnetic field. And this is the current, upward direction current. Force is inward. Force is inward. Force acts here inward. I am showing by cross sign. Or you can show the direction of force. Let's show the exact direction of force if you want. By cross symbol you can write, or you can show the direction of the force. It will be inward. Direction of the force will be inward. This is F1 vector. Okay. Then you come to BC. BC F2 force acts I whole into B vector cross B vector. Because its length is B. I have taken. Okay, L cross B, but its length is B. So where is the direction of force? The current is coming out. This is a 3D diagram also. The coil is kept like this, making some angle. The current is coming out. If current comes out, then where the direction of force? magnetic field this direction, current comes out. When it will be perpendicular, when it will be completely perpendicular, this coil will be perpendicular. Okay, then the current is coming out, force is in the upward direction. Force is in the upward direction here. This is the direction of the force. Along the axis of rotation, this is F2 vector. This is inward, perpendicular to the plane. This is upward, along the axis. Come to CD. Just like AB here also, F3 vector I whole into L cross B. And where is the direction of force? If current is coming downward direction, magnetic field is there, current is coming downward. Where is the force? You see. Where is the force? Force is now perpendicular to the plane in upward direction. This is F3 vector. This is perpendicular to the plane outward. Then DA, F4 vector. You neglect this gap, current goes like this, current comes like this. Okay. So I whole into B cross B. Where is the direction of force? If the current goes inside, inward, where is the direction of force? Magnetic field is like this, current goes inward. See, magnetic field is there, current goes inward. This is the direction of current inward. Thumb is downward. Thumb is downward, here downward. Along the axis. Can you mark? You will see the total force on this loop, F1 vector and F3 vector. F1 and F3, they are equal in magnitude and opposite in direction. They cancel each other. F2 vector, F3 vector, F2 and F4, sorry, F2 vector and F4 vector, they are equal in magnitude and also in opposite direction. So net force on the conductor is equal to 0. Means conductor will not move anywhere. Conductor will not move anywhere. But what happens here? You see, F2 and F4 vectors are in the same line. F4 is the downward direction. I have not shown F4. F4 and F2 and F4 are in the same line, so they cancel each other completely. They will not give any other effect. But F3 and F1, they are not in same line. You know, when two forces will not be same line, then what will happen? If one force will act here, if one force will act here in this direction, if one force will act here in this direction, what will happen? This one will rotate. This one will rotate. You know that in also electric dipole, in uniform electric field, torque acts here because these two forces are not in same line. You see, one force is in this direction, downward. One force is here in upward direction. Two forces are not in same line. But if two forces will be same line, net force will be 0, no turning effect. But if they will be in different line, then if they will be in different line, I have shown you like this. If they will be in different line, one is in upward direction and one is in downward direction, they will give the turning effect to this. Okay, so now this coil will rotate inside the uniform magnetic field. Now this coil will rotate, current carrying conductor inside uniform magnetic field. When you keep like this, the coil keep on rotating till the current flows through it. You are using this concept everywhere in your life. Everywhere in your life you are using this concept. This is the concept of your motor. This is the principle of a motor, electric motor. When a current carrying coil is placed in uniform magnetic field, it experiences torque due to which it rotates. Your fan, nothing is in your fan. Only one coil like this and a magnetic field is given. When you do the switch on, current passes through this coil and the coil rotates, and you have connected the blades to the coil and it starts rotating. Only nothing. The coil and magnetic field. Then it starts rotating. Everywhere anything rotates in our day-to-day life, in any devices, everywhere only this concept is used, the principle of motor. Everywhere it is used. So now let's come. What is the expression of the torque here? As these forces completely cancel, it has no role. This force completely cancel, it has no role. Only these two forces apply. Due to these two forces only torque comes. And what is the torque expression? magnitude of either force into perpendicular distance. This is the expression of torque you know in the lower classes, class 11. Magnitude of either force. What is the magnitude of this force? F1. This is B sin 90 means B. What the magnitude of this force F3? This is also B sin 90, so B. So magnitude of force torque is magnitude of either force into perpendicular distance. So magnitude of force is B into perpendicular distance. That one is important. You see, at point B we are applying the force in the downward direction. At point C the force is upward direction. C is a part of CD, B is a part of a B. At B downward, try to understand this one. At C it is upward. So I am drawing the figure here. So at C it is upward. I am showing the another figure. I am showing the direction to you. At C it is upward, and at B it is downward. You see, this is your which line? CB line. CB line. Here it is. Now this force is inward. This force is outward. I am showing here. Okay, and this is the magnetical line. And this angle is theta. Your coil makes theta angle with this. So what is the perpendicular distance between the two forces? Is this force F1, this force is F3. What is the perpendicular distance? So this is the perpendicular distance, this is CE. I am writing the name E. So this is the perpendicular distance between the two forces, CE. CE is the perpendicular distance and this is B. This is the breadth B, so C is nothing but B cos theta. So we can write here in place of C, we can write here B cos theta. Theta is the angle between surface of the coil and magnetic field. So now B I, so this is L into B. Length and breadth is nothing but area of the coil. So area of the coil into cos theta. So this is the expression of the torque on the current carrying loop in uniform magnetic field. But if this coil contains n number of turns, if the coil contains n number of turns, you multiply n there. You multiply n there. So if n number of turns, then you have to multiply n. Then torque is coming. Now torque is equal to now P-I-N-A cos theta. I am writing arranging like this. Why? You can able to remember easily. You can tell bina cos theta. Torque is equal to bina cos theta. This is the trick to remember the formula so that you can remember it for longer time. Torque on current carrying loop is bina cos theta. Sometimes some students ask the question, sir, I saw a book. In the book it is written that torque is bina sin theta. Yes. You will see in some books it is written bina sin theta. In some books it is written bina cos theta. I am telling also cos theta. Then is the cos theta wrong? Sin theta right? Is the sin theta wrong? Cos theta right? No, both are right. Both are right. How? The angle is different. The angle what we are taking, that is different. The angle is different here. Understand? So now let's see why the sin theta expression is there. Why the sin theta comes here? I am going to tell you about that sin theta. So I choose the theta angle between surface of coil and magnetic field. But if you choose, suppose I am taking the different angle, I am taking it phi, angle between aerial vector of a coil and magnetic field. Then what happens? Now see, theta plus phi. You see, the answer will be how much? Theta plus phi will be how much? Now you see. I am showing you that one. You take, suppose this is the coil. I am taking the help of this. This is your rectangular coil. Okay. This is the rectangular coil here. This one we are writing A. This point is A. This point is B. This point is C. This point is D. Right? This is the rectangular coil. Okay. And magnetic field is in which direction? Magnetic field, your magnetic field is now in this direction, towards this magnetic field. Magnetic field is towards this direction. You see, this is the magnetic field. Magnetic field, suppose coil, we have kept it like this. This is the direction of magnetic field. Okay, I am keeping the coil like this, it will be visible to you clearly. So this is the magnetic field. You see, magnetic field is this blue marker. Coil is this one. Coil is kept like this, making some angle with the magnetic field. Okay, so which angle is theta here? Between the coil and the magnetic field. See, this angle is theta. Between the coil, this is the magnetic field here. See, between the coil and the magnetic field, the angle is theta. This side angle is theta. But phi is the angle between aerial vector. Where is the direction of aerial vector? Perpendicular to it. This is the direction of aerial vector. See, aerial vector is always perpendicular to the surface. So what is phi? Angle between aerial vector and magnetic field means angle between the red marker and the blue marker. This is phi. You see? Again I am showing you. This is the coil. This is the magnetic field direction towards this. Magnetic field direction is towards this side. Coil is now making some angle. This angle is theta. But this is the aerial vector of the coil. Aerial vector makes how much angle with the magnetic field? Aerial vector of the coil makes how much angle with magnetic field? This angle. This is phi. Angle between the blue marker and the red marker is phi. Some books are taking this angle, some are taking this angle. Now in our derivation we choose this angle, but some books are taking the angle between magnetic field and aerial vector. This angle is phi. So if I remove the magnetic field is here, theta plus phi is how much you see. This is in the middle, this is theta and this side is phi. So theta plus phi is how much? You see, theta plus phi. Theta plus phi, now it becomes theta plus phi. Theta plus phi up to this theta, because magnetic field is here, then phi. Theta plus phi is how much? 90 degree. Theta plus phi will be 90 degree. If 90 degree, then theta is 90 minus phi. Now you see the expression of torque. Now you see the expression of torque. So torque is becoming beta. This is cos theta. It was cos theta. I am writing in place of theta 90 minus phi. Beta sin phi. Not required to confuse about this torque. Some books are writing cos theta. Those who are writing cos theta, they have taken the angle between surface of the coil and magnetic field. And those who are writing sin phi or sin theta, means they are taking the angle between aerial vector of the coil and magnetic field. If sin phi, then also if torque is a vector quantity, we can also write in vector form. You see, tau, this is V, this one is, rearrange this one, nia. Nia is the formula of which quantity? I told you, magnetic dipole moments. In circular coil, I have told you nia of a loop, current carrying loop dipole moment is nia. So this is sin phi. Or we can write this MB sin phi. This is also the direction of torque. This is also the expression of torque. Expression of torque. Now we can write it in vector form. Tau vector as a cross product is there. M vector cross B vector. This is the torque on a current carrying loop. In vector form. Tau vector is equal to M vector cross B vector. Torque on a current carrying loop.